All right, you guys, so today we're looking at scale diagrams, lesson 8.3. So moving on from looking at rates, but we will be using rates a little bit more in this lesson. So what is a scale diagram? Well, basically with a scale diagram, we have a drawing that is the same shape as whatever the original is that you're trying to copy, but it's either larger or smaller than the original. So essentially we do this, we make a scale diagram by ensuring that every dimension of the original was multiplied by some number, and then that makes the entire new drawing the same shape, but just of a different size. Now, it's important to be aware that when you're multiplying the sides, of course, they have to all be multiplied by the same number so that they're proportional, right? And when we multiply by that number, we call it a scale factor, okay? So scale factors are the factors by which each dimension in the original figure is multiplied, and they do not have units, okay? So it's just a ratio of the value in the diagram to the value in the original object or drawing that you were looking at. So scale factor is something that you can calculate by dividing those two things by each other. Make sure that you're aware that it's important that you always have the diagram divided by the original and not vice versa. So if you are going to be making an enlargement of the original, your scale factor value is always going to be greater than 1, whereas if you're doing a reduction, your scale factor is always going to be less than 1. And the reason these numbers center around the number 1 is because if you have something that is the exact same size, we call that a 1-to-1 ratio, right? And so basically that means if you have two things that are the same size, then if you divided their lengths by each other, they would equal 1. And so if they're larger, then they're going to be greater than that. If they're smaller, they're going to be less than that. So when you're drawing a scale drawing from an original object, make sure that you multiply every measurement by the scale factor so that you don't end up with kind of like, you know, some parts of the drawing bigger and some parts smaller, for example. And also just be aware of some of the calculations that we do. So if we're trying to make a diagram from an original, then we would take our original measurement, multiply it by our scale factor, and then that's going to give us the length that we would use for the diagram. However, if we already have a diagram and we're trying to figure out what the size of the original was, then you have to divide it by the scale factor so that you are determining what the original would be. Okay, so just like with rate, make sure that you're always using only multiplication and division in these types of calculations, never addition or subtraction. Okay, so in this example, we have every side of the original rectangle, which is this one here, was multiplied by 2 to create a scale drawing. Okay, so essentially this side here is 5 centimeters and this side here is 2.5 centimeters, and we want to be able to make a scale drawing by multiplying the measurements of our original by 2. So before we do the drawing, let's stop and think a second. Is the scale going to be, is the scale drawing going to be larger or smaller than the original? So if these sides are multiplied by 2, would it be larger or smaller? Well, of course, if you multiply by 2, then you're doubling. And so we would see that the scale drawing is going to be larger. And that's because our scale factor, which is 2, is greater than 1. Larger because scale factor is greater than 1. Whoops. Scale factor is greater than 1. Okay, the next thing is, what are the dimensions of our scale drawing? So remember, like we mentioned up here, if we want to determine the measurements of our diagram, we take our original measurement and multiply it by our scale factor. So the original measurements for this rectangle were 5 centimeters and our scale factor is 2, so we want to multiply that out. So we're going to have 10 centimeters, and then let's see, our other side is 2.5 centimeters. And we're going to double that, so we're going to have 5 centimeters. Okay, so if we were to draw our scale drawing, now unfortunately, if you guys have printed these notes, you might know that this isn't actually set up exactly perfectly, because it's kind of hard to actually get the exact measurements to work when you draw it in Word and then on the page. Or maybe I just need to learn that a little bit better. So I'm just going to double the actual measured size here. So that visually it looks like it's drawn to scale of double. Okay. Oh, why did that one end up being so off? Oh, I see. I did that. I measured the wrong one there. There we go. All right. So there's our scale drawing. It's a little bit off, as it usually will be if I draw it. And also I didn't have a T-square to make sure that the sides were done perfectly. But so let's just say that these are going to be our proper measurements. If that was true, then we would expect this side to be 10 centimeters long and this side here to be 5 centimeters long. Okay, so that would be our scale drawing. So that's a pretty straightforward one that you probably would have done previously in math classes. So let's look at going a little tiny bit more complicated. In this one, we are, instead of making a scale drawing or determining the new dimensions, we're already given the original drawing and then our scale drawing, and we're trying to figure out the scale factor. So this first one is pretty straightforward. Probably without doing any calculation, you can see what the scale factor would be if our original is 2 centimeters on each side and our scale drawing is 4 centimeters on each side. But let's just to get practice with using our actual calculations, we know that our scale factor is always going to be our diagram divided by our original, which was 2. And remember, your scale factor does not have to have units, so we end up with a scale factor of 2. Okay, and the other thing to kind of keep in mind is that if you had different lengths on the sides, you'd probably want to do the scale factor for all of the sides just to make sure that they were consistent. However, because these are the same on both sides, we don't have to do that. All right, let's have a look at these triangles. So this is where, because we have different measurements on the different sides of the triangle, we need to make sure that when we do our scale factor, we are comparing the same sides. Okay, so you wouldn't want to do like 10.5 divided by 3, for example, because that's not representing the same side of the triangle. So let's go through and do our scale factor. If we start with this side, we want to do the scale drawing, or diagram, divided by the original. So 10.5 divided by 7. And we find that that gives us 1.5. Okay, and then we do want to confirm with the other side. So the other side we have here is 4.5 divided by, the equivalent side on this triangle would be 3. And of course, that's also going to be 1.5. And just to be totally secure, let's do this last side. So 7.5 divided by 5, which of course is also 1.5. So we can confidently say that our scale factor is 1.5. All right, last one here. So in this case, a little bit different because we're going from a larger to a smaller, right? And so same rules apply, but we're just looking at a little bit of a different setup here. So let's start with the long side, for example. in our scale diagram, we have a side length of 9. And in our original, we had a size of 27. Now, if you want, you can type that into your calculator, but I would recommend that you become comfortable with using fractions. And so if you can recognize common factors for numbers, that's going to help you out with that. So if you can think of what the common factor would be here, hopefully you recognize that it's 9. 9 goes into 9 one time, and it goes into 27 3 times. So we can see that our scale diagram has a factor of a third, a scale factor of a third. And we should try the other side just to confirm. So starting out with 3 and comparing it to the original of 9. Again, the common factor in this one, if you picked 3, that's good. So 3 goes into 3 one time, and it goes into 9 3 times. So we have confirmation that our scale factor is. Now you can write it as a decimal if you want. 0.6 repeat, or sorry, 0.3 repeating. I'm thinking of 2/3. 0.3 repeating, or 1/3. Okay, so either one of those would be acceptable. So actually, if we wanted to, we could go back here and say, or 3/2 would work as well. Okay. All right. So that's kind of looking at calculating scale factor. Let's look at some of the different ways we can represent scale. So in a scale drawing, so you could have a map or a model, so that wouldn't really be a drawing, but you have a model of something, or in a diagram. The scale shows the relationship between the duplicate, the drawing or the model, and the actual object or drawing. So there's 4 ways to express the scale. The first one is a statement, where basically you're saying what on the diagram is equivalent to what in real life. So in this case, we'll say 1 centimeter is equal to 50 kilometers in real life. And we'll use this same comparison for all of these examples. The other way we can express it is as a rate. So we've already become pretty familiar with rates. Essentially, we're just writing the same values, but as a fraction. And you should just be aware that the numerator is always going to be the distance on the scale, and the denominator is always going to be the actual distance. We can also do a ratio where we're essentially doing the same thing. So 1, 2, but we represent it with the colon there. And the big difference here is that this is still actually talking about 50 kilometers, but if you remember, I mentioned in previous lessons that ratio is always a comparison of the same units. And so instead of having 50 kilometers, we have translated 50 kilometers into centimeters so that it's a ratio, right? Same units, 1 centimeter for every 5 million centimeters. Because the units are the same, they don't have to be stated in the ratio. The last way you could represent this is with a linear scale. So basically you have a kind of like a measurement here, and it's showing you the distances in real life on the bottom. And then you just use a ruler, or sometimes it'll say on there, but you can use a ruler to determine like how far the distance, like how far 1 centimeter is in real life. Okay, so again, I had a little bit of a trouble scaling it, but it should be about 1 centimeter, is represented by 50 kilometers there. Okay, and this is especially useful if you want to kind of get a visual sense of real distance. So the first number in any of these options always refers to the actual distance on the scale diagram. The second number always refers to the original distance. Okay, so just make sure you know first one is always the diagram. So let's go through some examples of each of these different ways of representing scale. The first one, we have the size of a kitchen measures about 3 centimeters by 5 centimeters on an architectural drawing. And the scale is given as 1 centimeters for every 1.5 meters. And we want to figure out what is the actual size of the kitchen. Okay, so if you recognize this from our previous lessons, we can think of this as being kind of like a rate, even though it's expressed as a statement here, right? So that's our kind of way of representing scale. I just had a little brain fart there. And the actual information we're given is, these are our two different measurements or our dimensions. Okay, so basically what we want to do is, personally I find it easier to just set this up a little bit like we already looked at in terms of rate. So 1 centimeter is equal to 1.5 meters in real life. This is, I mean, you can kind of pick your option. For me, what I even might do is skip the rate statement and just say, like, I know that 1 centimeter is 1.5. So of course then 2 centimeters is 3, 3 centimeters is 4.5, right? So I can just use logic. And then 5 centimeters would be an additional 3, so that would be 7.5. So if you can do your calculations like that, that's great. But maybe just so that you guys can see what I mean exactly, I'll just write it out. So if we think about this as our ratios like we've been talking about, 1 centimeter is 1.5 meters. And we know that that's going to be equal to, if we have 3 centimeters in our first part of the drawing, we want to know how many meters would that be. Well, to go from 1 centimeter to 3 centimeters, I have to do times by 3. And so that means I want to do the same thing down here. 1.5 meters times by 3 gives me 4.5 meters. Okay. The other one that we had there was for 1 centimeter, we have 1.5 meters, same ratio or rate, but we're setting it equal to, now on the diagram, we have 5 centimeters. And so, of course, if we want to get from 1 to 5 centimeters, we have to multiply by 5. If we do that to the top, we also need to do it to the bottom, and that gives us 7.5 meters. So then we can say the kitchen is 4.5 meters by 7.5 meters. Okay, so now we have our dimensions. So obviously more than one way to do these, so don't get too stressed out about doing it exactly the way I'm doing it, as long as you are consistently getting the correct answers, because then that means that the method that you're using is mathematically sound, right? Which is important, obviously. Okay, the next one we have here, we have scale on a map is given by the rate 1 centimeter per 50 kilometers. So this is kind of like the one we were looking at in the examples before. And just like we saw in the previous sets of notes, that's going to be our rate. Now, what is the actual information we're given? Well, we're told that a student measures the distance between Edmonton and Calgary on the map as 5.8 centimeters. Okay. So now we can think about how could we set this one up as a rate. Well, we have 1 centimeter for every 50 kilometers, right? The other thing you can think about here, just like I mentioned in the previous one, is if 1 centimeter is 50 kilometers, you have 5.8 centimeters. You probably know even before you set this up that we would be 5.8 times as much. So 5.8 times 50, well, 6 times 50 would be about 300. So we know we're going to be a little bit less than 300. So let's have a look at how that works out. We have 5.8 centimeters on the map. So that's going to give us how many kilometers? Well, 1 to get to 5.8, I need to multiply by 5.8. So that means I'm going to have to do the same thing here. 50 kilometers times by 5.8 is going to give me 290 kilometers. And we just estimated that if it was 6, it would be 300 kilometers. So we know that seems like we've done the math right. And actually in real life, if you have done much driving to Calgary, you probably know that that is actually about right. So the distance is 290 kilometers. Okay. All right, let's look at another one. So this one is a ratio. So this is getting a little bit trickier. The distance between two towns is 150 kilometers. If this distance was drawn on a map with a scale of 1 to 5 million, what is the measurement on the map? Okay, so the tricky part with this is remembering, like I told you, that this means that we have the same units here, okay? So essentially that means that our entire rate or ratio here is in centimeters. So you kind of have two options. You can either try and afterwards convert this into kilometers. I personally prefer to just work right away with converting kilometers into centimeters. I just find it's a little bit easier. So basically what I would do is I would do 150 kilometers. And if you remember back to the very first lesson, if you're going from kilometers to the base unit of meters, it's going to be times by 10 3 times. 1, 2, 3. And that brings you to your base unit. And then remember, centimeters is 2 more because there's decimeters and then centimeters. So times by 10 times by 10. And so that ends up giving us 15 million centimeters. Okay. So the reason why this is making things easier is because now I can set up my ratio as a rate where I have 1 to 5 million is equal to, and then I want to kind of think about, let's see, what is the measurement on the map? So I want to figure out, this is my measurement on the map, right? 1 centimeter for 50 kilometers, but measured in centimeters. So if this is my measurement on the map for the scale, then I want to have my measurement for the actual distance on the top as well. So that's going to be X centimeters out of 150 kilometers, which is in real life. So 15, 1, 2, 3, 1, 2, 3, 15 million. Now, the tricky part with this is because we don't have a direct, I mean, you probably can recognize that this would have to be multiplied by 3 because it's 5 million to 15 million. But if you weren't sure, you could do division, right? We talked about that in the lesson on rate, where you would take this amount and divide by that to figure out what the factor is. So 15 million divided by 5 million is going to give us 3. Okay, so essentially that's just telling us that you would have to do this times by 3, which means we would also have to do that to the top. And so we can say that we have 1 times by 3 gives us 3 centimeters on the map. Okay, and that makes sense, right? Because if 50 kilometers is represented here, and that's 1 centimeter, 50 times by 3 will give us 150. So the answer makes sense. Okay, just need to figure out where I am in my pages here. There we go. Second to last one here. So we have an example where a pool table measures 2.4 meters by 3.6 meters. If a ratio of 1, oh, sorry guys, I misplaced something there. If a ratio of 1 to 50 was used to create a scale drawing of the pool table, what would be the dimensions? Now, this one is a little bit unclear, but if you guys were in a test, I would make sure that that was clarified. So the ratio of 1 to 50, you're doing a smaller, like a scale drawing of it, right? So this is going to be measured in centimeters. So again, what we might want to do here is if we have meters and we know that our ratio is using centimeters, we might want to make these into centimeters right away just to make it easier. So we could say 2.4 meters, and we want to go to centimeters. So remember, this is our base unit. There's decimeters and then centimeters. So times by 10 gives us 240 centimeters. And 3.6 meters times by 10 gives us 360 centimeters. And so now we want to figure out our scale drawing, right? So we had 1 for every 50. Okay, so the 50 is going to be in real life because we're making a scale drawing that's going to be smaller. So we want to have our real life component of what we're trying to solve for on the bottom as well. So let's do the first dimension as 240. And so we want to figure out how many centimeters is that going to be. So again, we don't have a nice easy comparison here. So if we want to figure out the factor that this 50 is being increased by, we're going to do 240 divided by 50, which is going to give us 4.8 centimeters, or sorry, a factor of 4.8. But this is pretty easy too because it's to go from 1 to x. So basically what we're saying here is we need to multiply by 4.8, and of course that means we have to do it to the top as well. Okay, and so 1 times by 4.8 gives us 4.8 centimeters on the drawing. Okay, same thing for the 3.6. So we have a ratio of 1 to 50 still. Same ratio, of course, is equal to, we want to solve for how many centimeters on the drawing if there's 360 centimeters in real life. So same math because we don't have the nice conversion there. It's going to be 360 divided by 50, which will give us 7.2. And then same thing, 1 times by 7.2 gives us 7.2 centimeters in real life. Okay, so we can say the drawing is 4.8 centimeters by 7.2 centimeters. And basically all I did here was multiply by 7.2. Okay, last one here. So using the linear scale, determine the distance between Jasper Place and West Edmonton Mall. 1 centimeter on this scale is equal to 100. Now this one I got pretty close to being perfect. Okay, so with this one, essentially 1 centimeter is 100 meters. So here I have 1 centimeter. So that means that here I'm at 100 meters. So maybe I'll write that up here. I'm measuring in meters. 200, 300. These ones are getting a little bit off, but still the same. So 400. Okay, and then I can see that this last tick, which is where we're going to assume West Edmonton Mall is at 0.6. So then you would just kind of have to think if each one of these, like if you go from 3 to 4 is 100, that means, and there's 10 spaces between, right, a centimeter. So that means that if I go to 0.6, that means I have 460 there. Okay, so now just by measuring that, I can say it's 460 meters from Jasper Place to West Edmonton Mall. And that's my final answer. So with this one, it's nice and easy because all you have to do is do the measurement and then put in the value. Okay, so that's everything for scale drawings. You guys have a couple of questions that I have assigned you from the textbook that you can give a try there. And I will see you next time. We're going to look at our last section actually, which is I've kind of combined 8.5 and 8.6. And so we'll be looking a little bit more in depth kind of at scale diagrams, if I recall correctly. I don't have it right here in front of me. Yeah, we'll be looking at scale factors for 2D and 3D objects. So instead of looking at the linear components here, we'll be moving into like different types of shapes. All right, so I will see you then.